All right, we did it. We're done with sorting. So let's summarize. At the bottom, I'm going to show you the landscape of the sorting algorithms that we've studied. So the first flavor are comparison-based sorts. We had the selection, merge, partition, and insertion ideas. And we had this notion that we could optimize the selection sort idea by drawing inspiration from a heap, and that gave us heap sort. Okay? But these were the four key ideas that we had for comparison-based sorting. Next, we had alphabet-based sorting items from a small alphabet, or equivalently integers. Any alphabet can be converted into the set of integers trivially. So like spade, diamond, club, heart is just 1, 2, 3, 4, or 0, 1, 2, 3. And that was our counting sort. So that's one example of a small alphabet sorting algorithm. There are others. And then the third approach was a radix-based sort, where we had two flavors, LSD and MSD, and they used counting sort as a subroutine. Right? We used counting sort to sort by each digit. Now, each of these, as we've seen, they can be useful in different circumstances. But being able to tell, should I be using LSD radix sort or quick sort, is actually quite hard. It's very, very tricky. And it requires computational experiment, and it's really not something you could prove in advance often. I mean, you can show maybe that selection sorts in squared, so it's never going to be better than merge sort in really any case. But in general, to refine and find the best sort, it takes a ton of work, mostly empirical. Now, the point here was not to give you all these sorts so that, oh, for this task, use selection sort. For this one, use radix sort. I mean, that's a neat side effect that might be useful to you. But really, the reason I taught you all this stuff is because I want to teach you how to approach problems in general. And this gives you a huge variety of different approaches to the same simple problem. And I hope you found it useful. Now, we've also, that we've finished sorting, I will now say that earlier, the other problem we studied, the other big one, was, I mentioned it was called the search problem. So in the search problem, which we focused on in the data structures lectures, we were trying to retrieve data of interest. So for example, a list, a map, a set, a priority queue, and a disjoint sets object. Those are all different ways to solve a very generic problem known as the search problem, where, for example, with a list, we want to be able to retrieve by index, or for maps and sets, we want to be able to retrieve by key identity. Like I want to get the item corresponding to dog or whatever. That would be a map. So there's some interesting connections between the sort problem and the search problem. So I put them together on this slide. So here are our search by key identity data structures. We have so I'm only showing sets and maps, so and each of the different ideas when we want to search by key identity. We have our 2-3 tree, our red-black tree. Those are both basically ultimately going to be like our comparison sorts. We have our separate chaining idea, our hash table idea, and then we had tries. So I've already here kind of I'm foreshadowing the connections here. But basically here, our comparison-based sorts, our alphabet-based sorts, and our radix-based sorts can be thought of as analogs of these three up top. So for example, the 2-3 tree and red-black tree, these are analogous to comparison-based because they use comparisons to keep the information organized in the search problem. And in the sorting case, it uses comparisons to bring things into order. So there's a deep connection here. Now, hash tables you could think of as kind of like counting sort. It's not as clear a connection, but it is somewhat analogous to integer sorting. You use hash code and equals to keep your information in order. But with counting, well, you do something else where you're exploiting space in order to save time. In that sense, it's an analog. And then lastly, our tries, which allowed us to search digit by digit, that was roughly analogous to radix sorting. Now that we know all of that, right? I mean, this is the picture maybe to have in your mind. If you say, what did I learn in this class? There's only a subset because we've only talked about the search by key identity data structures. But this is the sort of thing that if you come back and be a lab assistant or a TA or someday teach this class as an instructor, you'll start to feel all these connections and see that this is the landscape. So to wrap up today, I'll just say there's plenty more to explore, right? We've finished our discussion of searching and sorting, but there's so much else you can do. There's other directions you can do, like probabilistic identity structures, like skip lists. But you can also mix and match these ideas in funny ways. So I'll just throw out a few questions I think are pretty interesting that you might consider. And they'll be on the study guides. They are, in fact, already on the study guides. So one is, we didn't have to use counting as our subroutine here. What if we used quicksort instead? Like, what if we did MSD radix sort where we're quick sorting on each digit? Does that make sense? Is it faster? What is that thing? Another, Well, we saw that if we implement comparable, we get a compare to method, which means that we can now put those objects in a 2-3 tree or a red-black tree. And we can also do comparison-based sorts. So by implementing comparison, those objects are now eligible to interact with this beautiful idea and all of these beautiful ideas. Is there something similar, given that there's an analog between radix sorting and tries? Is there some single interface that would allow you to store something in a try and radix sort? What would that interface look like? What is it? Is that something that could exist, should exist? And another, let's say we have an object that has digits, right? It has some notion that it could be broken into pieces, and that it is also comparable. Could we somehow use an LLRB to improve radix sort in some way? That is, it can be compared and it has the ability to be broken into digits. Is there some way to optimize or do something interesting, like give additional functionality, improve speed, improve memory, who knows what? There's so many things out there, and field's wide open. All right, so that concludes our sorting and our data structures part of the class. Coming up, we're going to do some extra special topics, a little more software engineering, but for our purposes this semester, we're good to go. That's it. All right, see you next video.